In this video, I'd like to show you that those vectors x1 and x2 are guaranteed to be perpendicular to each other. We know the following. We know that y1 is equal to a multiplied by x1. We also know that y2 is equal to a multiplied by x2. This means that x1 is equal to a minus 1 multiplied by y1. Also, x2 is equal to a minus 1 multiplied by y2. Now, I want to prove that x1 must be perpendicular to x2. This means that the dot product between x1 and x2 must be equal to 0. So I want to get the value for the dot product x1 transposed multiplied by x2. This is equal to a minus 1 y1 transposed multiplied by a minus 1 y2, and this is equal to y1 transposed a minus 1 transposed multiplied by a minus 1 multiplied by y2. This is again equal to y1 transposed a transposed minus 1 a minus 1 multiplied by y2, and this is equal to y1 transposed a transposed all inverse multiplied by y2, and this is equal to some scalar because this is a matrix multiplied by a vector producing a vector. Then this vector multiplied by a row will give you a scalar value, and so this is equal to some scalar value a. And our goal now is to prove that this value a is actually equal to 0. Now, what do we know about this a transpose? In fact, this is the covariance matrix of the data after the transformation. Let's see why. Here, we assume that the original data right here was normally distributed, and so the covariance matrix right here was equal to the identity matrix. Now, I want to get the covariance matrix in this space. So we see that the y data points are equal to a multiplied by the x data points, where the x matrix has all the points on the circle. So x vector or the x matrix is equal to x1, x2 up to xn. So y is equal to y1, y2 up to yn again. Now I want the covariance matrix of the data after the transformation, and I am assuming that my data is already centered. So the covariance matrix after the transformation is equal to 1 over n multiplied by y transpose, and this is equal to 1 over n ax multiplied by ax all transposed. And so this is equal to 1 over n ax x transposed a transposed, and this is equal to a x transposed over n multiplied by a transposed on the other side multiplied by a transposed. But this right here, this term right here, is actually equal to the covariance matrix of the data before the transformation, and this is equal to I. So the covariance matrix is equal to a transposed. Very well. Now this means that x1 transposed x2 is equal to y1 transposed sigma minus 1 y2. And we know that y1 and y2 are actually eigenvectors of the covariance matrix sigma. We know this piece of information from the BCA section. Now here is another fact. The eigenvectors of a matrix are the same as the eigenvectors of the inverse of this matrix. It is actually easy to prove such statement in many ways. One way to prove this statement is that we know intuitively that the matrix sigma, if applied on one of its eigenvectors, let's say y1, it will scale this vector by an amount of lambda reaching lambda y1 vector. Now we know that the inverse of any matrix must reverse the operation performed by this matrix. And so the matrix sigma minus 1 should take this lambda y1 vector and scale it by an amount of 1 over lambda in order to get the vector y1 again. But you see that the matrix sigma minus 1 has operated on this lambda y1 vector and got another vector in the same direction but scaled by some amount. This means that the y1 direction is also an eigenvector for this matrix sigma minus 1. This is one reasoning. Another reasoning is that we know that sigma is equal to Q D Q transpose. Now sigma minus 1 is equal to this minus 1, which is equal to Q D minus 1 Q transpose. Now this is the matrix of eigenvectors of the matrix sigma. This is the matrix of eigenvectors of the matrix sigma minus 1, and we can easily see that this Q is the same, meaning that all the eigenvectors are the same. A third reasoning for the same statement might be as follows. We know that the equation for the eigenvectors is A multiplied by Y is equal to lambda multiplied by Y. Now, assuming that the matrix A does have an inverse, then multiplying A minus 1 on both sides, you will find that Y is equal to lambda multiplied by A inverse Y. This means that A inverse Y is equal to 1 over lambda multiplied by Y. This means that A minus 1 multiplied by some vector is equal to some scaling factor multiplied by the same vector. Again, meaning that Y is also an eigenvector for the matrix sigma minus 1, or A minus 1 in this case. So this means that Y1 and Y2 are both eigenvectors for the matrix sigma minus 1. So actually this is equal to Y1 transposed multiplied by 1 over lambda 2, where lambda 2 is the eigenvalue of the original matrix sigma multiplied by Y2, and this is equal to 1 over lambda 2 Y1 transposed Y2, and this is clearly equal to 0 since Y1 and Y2 are perpendicular to each other. So I have proven the fact that if Y1 and Y2 are eigenvectors of the covariance matrix, then Y1 transpose X2 will certainly be equal to 0, and so X1 and X2 will be perpendicular to each other as desired.